With regular integrals, not only could we find area under a curve, but we could also find the length of that curve. With double integrals, we know how to find the volume under a surface. Now we're going to solve the similar problem of finding the area of that surface, so the surface area. Let's say we have a function, f of x, y, over some region D. So there's some region in the plane that we're going to find, that will take this function and make it into a surface over that region, and we'll find the area of that region, not the volume underneath it. As an example, let's go ahead and take the function f of xy is equal to 2 minus x squared minus y squared, and we'll go ahead and graph this function. So what we get is a paraboloid. I'm going to go ahead and zoom in. We're going to be taking a region around the origin. I'm not really going to specify what region that is, but we're going to be looking at a region around the origin. And we're going to see how could we even approach this question of surface area. Well, just similar to how we were doing all the volume and stuff before, what we're going to do is we're going to take our region D and we're going to divide it up into a bunch of subrectangles. Now, the book approaches this from D being a rectangle originally and then kind of generalizing later. For now, since all we're really trying to do is derive a formula, we're not going to worry too much about what the region D looks like. So we're going to divide D into subrectangles. Rij. So I'm just going to use Rij as notation for the rectangle that we're going to be looking at throughout most of this, and we'll derive a formula for that subrectangle that we will then kind of just generalize over all the rectangles. Of course, on Rij, we need to take a sample point, though in this particular case, we're going to pick a particular point. So we're going to say that the point xiyj is a point in Rij, really just one of the corners that's closest to the origin. So let's actually put a rectangle into our picture here. I'm going to take as our rectangle the rectangle starting at 1/2, 1/2, going over to 0.11. So I'm just going to go ahead and put in those points. So 1/2, 1/2. It'll be down in the XY plane, so it'll be a little hard to see right off the bat. Well, 1/2, 1/2, 1/2, 1, 1, 1/2, and 1, 1. Those are going to be the vertices of my rectangle. In this case, a square, actually. I don't really want them to be quite as big as they put them. We also don't need the labels. I'm going to go ahead and actually make it the square. So polygon with those points, A, B, D, C, depending in that order, so it actually goes around our square. Okay, so we've got this square. We're trying to find the surface area over that. In fact, I'm going to go ahead and essentially project that square onto the surface so we see exactly what part of the surface we're actually looking at. So you might have been able to tell already from the grid lines that GeoGebra automatically puts in there, but now you can very easily see exactly what portion of the surface that we're really looking at over this square. Now, how are we actually going to find the area of that section? Well, we're going to approximate, just like we've been approximating volumes. And what we're going to do is use our point. So in this case, because the closest point of our square to the origin is the point 1/2, 1/2, we're going to look at the point above that. So it's 1/2, 1/2, 3/2, and we're going to take the tangent plane at that point. Now we can compute tangent planes, remember, using the derivative. So here, for this particular function, f sub x is negative 2x, f sub y is negative 2y. Hopefully you know how to do that by now. At the point 1/2, 1/2, the derivative with respect to x is going to be negative 2 times 1/2, so it's going to be negative 1. And same thing with f sub y. You get negative 1. And so our tangent plane is going to have the equation. So it says this negative 1 times x plus negative 1 times y minus z, so the minus z is always the same, is equal to some value over here. Normally when we do this, we can actually just go ahead and plug in a point. So I mentioned here that 1/2, 1/2, 3/2 is the point that we're trying to find the tangent plane at. So we'll go ahead and take those values and plug them into negative x minus y minus z. We get negative 5/2. Of course, everything, we don't need a negative here, so I'm going to go ahead and make everything positive. So those will go away, and these will become plus signs. And then we'll go ahead and put that plane in here. So that is definitely tangent to the surface at 1/2, 1/2, 3/2. In fact, I'm going to go ahead and even put that point in here. So it's tangent at that point. And now I'm going to look at the portion of the surface that is above, the portion of this new surface, this plane, that is above our square. So the section of the plane that is above that square is this parallelogram that we have on here. In fact, we can even take out the plane so maybe you can see it a little bit better. We're approximating the surface by the area of that parallelogram. You can kind of see it there. We are going to refer to that, so the area of the parallelogram over Rij, we're going to call that delta Tij, just to kind of go along with how the book set this up. And so we can essentially turn this into a Riemann sum, where the area of our surface is just a double sum over a bunch of these parallelograms that are approximating our surface. And that obviously that approximation gets better as our parallelograms get smaller, as they're covering less of our base domain. So this right here doesn't approximate it incredibly well, but if we were looking at a smaller piece, it would approximate it better. The approximation is definitely better up near the point that we use rather than down here where it's further off. But in order to actually do this, we want to find a formula for what this delta Tij actually is. It is a parallelogram. So we do know from back in chapter 12, a formula for the area of a parallelogram. It's the magnitude of the cross product of A and B, where A and B are two sides of our parallelogram. These are vectors A and B. So if we have vectors A and B based at the same point, they form a parallelogram. Let me make this actually a little bit better than In fact, these other sides are actually the same. This is another copy of B. This is another copy of A. We get a parallelogram here, and the area of that thing is the magnitude of A crossed with B. Now, how do we use that here? Well, keep in mind that what we're dealing with here are tangent. These two sides that are close to our point that we're using are both tangent lines to the surface through that point. And they're specifically the tangent lines that are parallel to the x-axis and the y-axis. That means you can say that we're dealing with slopes that are given by the partial derivatives. If we start with the one that's parallel to the x-axis, this one here, then our change in z is given. Well, first of all, I should note here that stop trying to rotate on your own. We're saying that the x width of our rectangle here, in this case is 1/2. We're going to call that delta x as our difference in x's. Well, obviously the difference in our y's is 0 because we're choosing the one that's parallel to the x-axis. And we're concerned mostly with how far down does it go. What is the change in our z value? Well, because we're dealing with a line, basically by the point slope formula, the change in our z's is equal to the derivative with respect to x at that point. Remember that point we're denoting it as xi, yj, times the difference in our x's. Therefore, we could basically say that our vector A is the vector where we have, actually, yeah, should put this in terms of I, j, and k. Our change in our x's is delta x, that's times I. Technically we have 0 j's, just put that in there to remind you. And then our change in our z's is this formula here. And I'm just going to go ahead and abbreviate f sub x of xi yj by just f sub x. We'll put the point back in a little bit later. But for the moment, I want to be able to simplify what we're writing down. For our other side, we're going to do exactly the same thing, except now the change in x is going to be 0, the change in y is going to be delta y, and we'll use a similar formula, except we're going to use the derivative with respect to y instead. So this time it's going to be 0 times I, delta y times j, and then f sub y times delta y, k. When we take the cross product, we'll just go ahead and put these in there. And we'd like to simplify that before we try to take the magnitude. Well, first thing to note here, this first vector is all multiplied by delta x. There's one of the formulas for dealing with cross products says that if we have a multiple of one of our vectors, we can pull it out. So let's just go ahead and pull the delta x out from this first term, this first factor. We can do the same thing with delta y for our second factor. And that'll save us some work overall. So this first one, once we pull out the delta x, we have I plus s of x times k. This one we have j plus f sub y times k. And then I'm going to put the delta x, delta y at the back. When we go ahead and actually do this computation, the fact that we did have zeros there does help us out a good amount. So we'll have, I'm going to start with the f sub x times k crossed with j. There, the f sub x is going to stay there. K crossed with j, if you remember, that turns into a negative I. So we actually get a negative f sub x times I. The I times f sub y times k, so I crossed with k, that turns into a negative j, so we get a minus f sub y j. The I crossed with j actually turns into a positive k, so you have plus k. And then f sub x times k crossed with f sub y times k. K crossed with k is 0, so that one's not in there. Delta x times delta y. Now we're actually these are the two side lengths of our rectangle. These are the side lengths of rij. That means we can just basically write that as delta a, or maybe delta aij if we want to be specific. If we take the magnitude of this thing, the delta aij is not a vector. It's a scalar that we can pull out. And here, this is just written in terms of I, j, and k. We use our Pythagorean identity, or the Pythagorean theorem type way of computing the magnitude of vectors. We take our first factor here, we square it, add to the second factor, squared, and so on, and then we take the square root of all that. So we'll end up here with the square root of f sub x squared plus f sub y squared plus 1. Then we have the delta a at the end. Of course, these f sub x and f sub y's are at the point xi, yj. But the point here is now we have a formula for delta t, ij. Because this is just the area of the parallelogram that we're trying to find. And so we have a formula for this, the surface area in terms of an integral. So we're taking we essentially take this form that we have here. We're putting that into our, it's here. We're putting that into our Riemann sum, and then turning that Riemann sum into a double integral. And so we get this formula here for the surface area in terms of the derivatives of f, both f sub x and f sub y, over that region D. We can also write this as this, where we're using the curly D notation rather than the f sub x and f sub y. They rearranged it and put the 1 in front. Not that that really makes much of a difference. And these are really just the same formulas using different notations. But one thing that they wanted you to note here, the formula that we have for the surface area is actually very similar to the formula that we had for arc length back in chapter 8. There we could say that the length of the curve of some, if we were graphing, say, y equals f of x, the length of that curve would be the integral from starting point A to ending point B of the square root of 1 plus the derivative squared dx. These are very similar expressions. Alright, so the main thing here for this section is that we have these formulas. Or really, we just have one formula for surface area that we're going to go ahead and apply. So let's just jump right into some examples. We'll go ahead and start off with problem 3. Here we're looking for the area of the part of the plane 3x plus 2y plus z equals 6 that lies in the first octant. Let's go ahead and graph that. We have a plane. As you can tell, it does hit our x, y, and z axes at 2, 3, and 6. So there's a part that's in this first octant over here, and it goes off to infinity in the other octants. It's a little hard to see exactly where it's intersecting our axes, so let's go ahead and actually put those in here. So they call the plane A. So we're going to intersect A with the x-axis. Sorry, the xy plane is z equals 0. We can do the same thing with our other ones. So have x equals 0 and y equals 0. Those are the intersections of our plane with the three coordinate planes. So the area that we're trying to look at is the part that's contained inside of all three of these lines. It's this triangle that we have in here. And we need to know what are we going to integrate over in order to get the area of that surface. And we can just kind of look down straight at the xy plane and see what actually lies underneath that surface. It's this triangle here. It's a nice right triangle, in fact. And we're going to set that up as a double integral. So, well, first of all, we need to solve this for z. So this is actually the function that we have over that triangle. Remember our formula, we take the derivative of z with respect to both x and y. So the derivative of z with respect to x, in this case, is just a -3, regardless of what point we're at. Similarly with y, we just get a -2. So our area, the surface, is going to be the double integral over our triangle. Let's call it t, just to be kind of cute with it. We'll have 1 plus -3 squared is 9, plus -2 squared is 4, which actually simplifies fairly nicely to the square root of 14. And we can even pull out that square root of 14. Now, at this point, we could set up our double integral. Our domain here, remember, is our triangle. We can actually view this as either type 1 or type 2. Both of them work. But we can actually simplify this problem a lot by remembering that when we're integrating 1 over some region, the result of that is just going to give us the area of that region. Since our region is just a triangle, this double integral is just the area of this triangle. And it's actually a right triangle. We know that our plane is actually intersecting our x-axis at 2 and our y-axis at 3, so it's a right triangle with a base of 2 and a height of 3. We can find that area really easily. So you can say the area of t is just half of 3 times 2, or just 3. And so our double integral is just going to be 3 times the square root of 14. Now, don't expect it to always work out that easily. Most of the time, we will not get a constant in here. That only worked because both of our derivatives turned out to be constants. And that happens because we're dealing with a plane. So if we're dealing with a surface that is given by a plane over a region, we might expect to be able to do something like this. But in general, we're not going to be able to. So just a nice simple example to start. Alright, next problem is problem 5. We're going to look at the part of a paraboloid. So that's actually pretty similar to the paraboloid that we looked at initially, except we're actually down 1. So we have this paraboloid 1 minus x squared minus y squared that lies above the plane z equals -2. So again, might as well start off by first graphing it. So we have our paraboloid here. We're going to take the plane z equals -2. So it's a plane down below the x-axis, or the x, sorry, should say the xy plane, that kind of cuts off a part of our paraboloid. We're looking at what is the surface area of the point. Of course, one of our first questions is what exactly is the domain of integration? If we look at it from above, we can see that it's supposed to be a disk, but we're going to have to figure out exactly what is this boundary that we're going to be looking at. And really that just means, what does the intersection look like? If we let z equal -2 in this formula, we have -2 equals 1 minus x squared minus y squared. Or if we bring the x squared y squared over to the other side, and the -2 over to here, we're looking at x squared plus y squared equals 3. That's the equation of a circle, as we would expect, and it has a radius of actually square root of 3. And that's going to be the domain that we're going to be looking at. Well, we need to go ahead and find what are the derivatives of this function with respect to both x and y. Derivative of this with respect to x is -2x. The derivative with respect to y is -2y. So that means the area of our surface is going to be the double integral over the domain, this disk that we're talking about, of the square root of 1 plus -2x squared, so 4x squared, plus -2y squared, so plus 4y squared, dA. Of course, since we are working with a domain that is a circle around the origin, it actually would make sense to use polar coordinates. So don't forget that we can use polar coordinates in these examples still. In polar coordinates, what does this actually become? Well, we're going all the way around the circle, so theta is going to be between 0 and 2 pi. And then r is going to start at 0 at the origin, and then it goes out to this circle, which again has a radius of square root of 3. That means we can write this as integral from 0 to 2 pi, integral from 0 to square root 3. Remember, x squared plus y squared is equal to r squared, so that makes this integrand really nice and easy to set up. This is just going to be the integral of 1 plus 4r squared. Don't forget our extra r. We have dr d theta. Now since we just have numbers for our limits, and there's no thetas in the integrand, we can go ahead and immediately take care of the d theta part. That just turns into 2 pi outside. All the stuff with the r, we can go ahead and use a substitution there. We have u equals 1 plus 4r squared. That means that du is going to be 8r dr. That extra r actually comes in handy for us. We're going to have to go ahead and divide by 8, though, to actually make this work. So we'll divide that by 8. This will become the square root of u du. And then what are our new limits? We're going to go ahead and plug in 0 and square root of 3 into our formula for u. When r equals 0, u equals 1. When r equals square root of 3, then r squared is 3. 4 times 3 is 12, plus 1 is a 13. You're just going to reduce this to pi over 4. This integral, the integral of square root of u, is going to be, well, we're going to raise the power of 1/2 to 3/2, and then we divide by the new power, so we multiply by 2/3. We're going to take that from 1 to 13. I'm actually going to go ahead and combine the 2/3 with the pi over 2, or sorry, the pi over 4. The 2's will cancel out a 2, so we'll have pi over 2 times 1/3, or pi over 6. Then we have 13 to the 3/2. I like to write that as 13 square root of 13. Not really any more simplification we can do there. But then 1 to the 3 halves is 1. And that's our formula for the area of this surface. The area of this little cap here is exactly pi over 6 times 13 radical 13 minus 1. Next, let's move on to problem 8. Here we're given a surface, kind of a complicated looking surface, but it's really just 2/3 times the sum of two powers, a power of x and a power of y. They actually already gave us our domain. It's just this time it's going to be the box, which we could go ahead and write as 0, 1 cross with 0, 1. And we just want to find what is the actual surface area of that surface. Of course, we can go ahead and graph it first. So we have 2/3 times x to the 3 halves plus y to the 3 halves. Okay. For some reason, GeoGebra doesn't really like that, so let's kind of force it to be a function. Last time it tried to do it as a curve for some reason. Oh, oops. Forgot my caret to turn that into a power. There we go. We have this surface. Note that we only have part in the first quadrant here because we have x to the 3 halves. That is a square root, so we can't have any negative x's. Same thing for y. So we only have this portion that's in when x and y are both positive, and the result always turns out to be positive. So we just have this thing that starts at the origin and kind of goes up from there. We're going to be looking at the part that's inside the square from 0 to 1, 0 to 1. Actually, you can kind of see that that's this box that they already have a grid line for. And we want to know what is the area of that piece. Well, following the formulas that we had from before, we need to look at the derivatives of z with respect to x and y. Now, this is actually not as complicated as it might look initially because this is just the sum of a function of x and a function of y. When we take the partial derivative with respect to x, the y part doesn't matter. We're just differentiating this power of x. And the derivative of x to the 3 halves is just 3 halves x to the 1 half. But then the 2/3 out in front actually gets rid of the 3 halves. So really just this is x to the 1 half, or if you prefer, you can write that as square root of x. Same thing with y. Everything's nice and symmetric here. Get y to the 1 half, or square root of y. That means the area of the surface is the double integral. Well, actually, I'm not even going to write it as the double integral over some domain. We already know that domain is just a rectangle, or a square specifically here. So I'm just going to go ahead and write that as the integral from 0 to 1, integral from 0 to 1, of the square root of 1 plus square root of x squared is x, square root of y squared is y. So we just had the square root of 1 plus x plus y, dy dx. Really nice formula. Now we go ahead and actually just find the integral like we normally would. We have this thing, the square root of this thing, when we actually integrate that with respect to y. Technically, we're doing a substitution here of u equals 1 plus x plus y, but because du there is just going to be dy, we don't really have to worry too much about it. We're just going to get what we have inside here, treat it as our variable. We have the square root of u. When we take the integral of that, we get u to the 3 halves power times the reciprocal of our new power. That's going to go from 0 to 1. Of course, u here is not u. It's actually 1 plus x plus y. And I didn't rewrite these in terms of u. So really what we're looking at here is well, might as well pull out the 2/3. We have when y equals 1, u is equal to 1 plus x plus 1, or 2 plus x. When y equals 0, u is just going to be 1 plus x. Maybe I should go ahead and specify here that we are looking at y equals 0 to y equals 1. Now we get to integrate this thing. We do the same kind of thing where we set u equal to what we have inside of those. Then we actually do exactly the same kind of thing. But the same thing is going to happen where what happens inside there really doesn't matter too much. It doesn't actually change. We're going to have 2 plus x to 1 more than 3 halves is 5 halves. Then when we multiply by the reciprocal, we get a 2/5. Exactly the same thing happens here. In fact, everything's the same except instead of a 2 that didn't change anything on the outside, we have a 1 that's not going to change anything on the outside. So we're still going to get a 2/5 times 1 plus x to the 5 halves. And the x is going to go from 0 to 1. Again, I'm going to go ahead and pull out this extra factor. So we have a 2/3 times a 2/5. That's factored out of all that. So we have a 4 over 15. On the inside, what happens when we plug in 1 here? We have 2 plus 1, so 3 to the 5 halves. Actually, I'm even going to go ahead and write this as, remember, 5 halves is 2.5. So really this is 3 squared times square root of 3. So we have a 9 root 3. Then when we plug in 1 here, we have 2 to the 5 halves, or 4 root 2. When we plug 0 into here, again, the 2/5 is already outside. It's already factored out. So we're going to have 2 to the 5 halves, or another negative 4 square root 2. I'm just going to go ahead and combine those right away. So we have an 8 square root 2. And then finally, we plug in 0 here. We have a 1 to the 5 halves, or just 1, but we are subtracting the negative 1, so we add 1. And that's as simple as we can write it out. This is our result. 4/5 times this thing involving 2 different square roots. Let's do one last example. Problem 9. We want to find the area of the surface z equals x times y that is inside the cylinder x squared plus y squared equals 1. Of course, like we've been doing on all of them so far, we're going to go ahead and graph this first. So first of all, let's graph the cylinder. So we're only going to be concerned with the stuff that's inside the cylinder. If we graph the surface, z equals x times y, we get this nice big thing. But of course, we're only really concerned with what's happening inside the actual cylinder. So maybe we'll even go ahead and use an if statement to actually restrict what we're looking at. So we're only looking at the part that's inside the cylinder. In fact, I'm going to even leave out that cylinder. We've got this piece here that we want to find the area of. What is the area of this essentially Pringles chip? Now, one thing to note here that we didn't really pay attention to before, this surface is going below the xy plane. When the book initially sets up the formula for the surface area, it does insist that we have a function that is non-negative, that's all above the xy plane. That's not really too important, and it actually doesn't change our formula. So I didn't even bother including that initial assumption when we constructed it. But I just wanted to note that their initial assumption there is not really necessary for anything that we're doing here. But we're just going to go ahead and use this we're going to find the area that's just like we've been doing the other ones. One thing to note, we do want to worry about what is our domain of integration. That should be pretty obvious that we're using the cylinder as our boundary. We're looking at integrating over the unit disk, where our function is z equals x times y. So we can say d here is a set of points r theta, where of course theta goes all the way around the circle, and r goes from 0 at the origin to 1 at that boundary. We're going to need to look at what are the derivatives of z with respect to x and y. Derivative of z with respect to x is y. Derivative of z with respect to y is x. The area of our surface is a double integral over d of the square root of 1 plus y squared plus x squared. Now, how do we integrate over a disk? Should be fairly obvious because we did this just a couple examples ago. We might as well go ahead and use some polar coordinates. Plus, in that regard, this y squared plus x squared is just r squared. So we have the integral from 0 to 2 pi, integral from 0 to 1, of the square root of 1 plus r squared. We have our extra r. We have a dr d theta. Of course, we can go ahead and, since we're only dealing with numbers as our limits, and we don't have any thetas inside, the integral with respect to theta just becomes a 2 pi on the outside. To deal with the square root of 1 plus r squared times r, we can make a substitution again. Very similar to what we did last time. That means u equals 1 plus r squared. Du is going to be 2r dr. We already have the r. And in fact, we can go ahead and steal this 2 that we got from the integral with respect to theta. So let's turn that into a pi on the outside. On the inside, this just turns into a square root of u du. Our limits have to change. Instead of going from 0 to 1, when we plug that into the formula for 1 plus r squared, well, when r is 0, we get 1. When r is 1, we get 2. So this already has greatly simplified down to a very, very easy integral to do. Integral of square root of u. We've done integrals of square roots many times already this video. We end up with u to the 3/2 power times 2/3. Our limits are still 1 to 2. Go ahead and pull out the 2/3, so we have a 2 pi over 3. When we plug in 2 to the 3/2 power is 2 square root 2. 1 to the 3/2 power is just 1. And again, there's not really any more simplification we can do. So there we have it. Working with the formula for surface area is really not all that complicated. I mean, actually, a lot of these problems, it was just how do you set up the domain, and that's stuff that we've been working with for the last few sets of videos, the last few sections. And they're not going to give you anything that you can't actually integrate. There are some problems that the book actually has where it expects you to actually approximate, where maybe the integral itself is not something you can do very easily, but I haven't assigned any of those to you, because it's more just being, if you can set it up, if you can't do the integration, you can just fall back on any numerical integration ideas that we had from back in Calc 1 or Calc 2. That's not really too much of an interest to me in this particular chapter. So I'm going to go ahead and leave it off here. Kind of a longer video just because I put it all into one video this time. But this was really just one application, like the like we had multiple applications from the last section, so I didn't really want to split it all up. But I'll see you guys in the next video, where we're going to actually do something a little bit different. We're not going to be working with double integrals next time. So I'll see you there.